Let us look at this problem right here. We have a box that is placed at a corner, say a corner of a table, for instance, and that is from point E to C. We have a distance A, and that distance is 200 millimeters. Remember that 200 millimeters is anytime that you have this international system of units. This is international system of units, system of international units. You are talking about forces in newtons. And newtons, we talked about this the first day. Force is the mass of a system, of a particle, of whatever you're dealing with, times acceleration. That's why, for instance, light is so interesting, because it has photons which have no mass. Photons are massless particles, but still they have forces. So that's the difference between mechanics and quantum mechanics. Quantum mechanics and classical mechanics. Here we're talking about classical mechanics. In an international system of units, you always have a mass, and that is in kilograms. And the acceleration is in meters per second square. So time will always be given in, well, unless they give it in milliseconds, you have to take it to seconds. And if they give it in millimeters, you have to take it to meters. So 200 millimeters times 1,000 millimeters is 1 meter. Therefore, we are talking about 0.2 meters. So this distance is 0.2 meters. Always take your distances to meters, your forces to newtons, your masses to kilograms, so on and so forth. Okay, so the weight of the crate of the box is 50 kilograms. So it's already kilograms, that's good. And they're applying a force P. The complication here is that P has an angle. It's not straight, has an angle with respect to the horizontal axis. So we can already see that this is going to be X and this is going to be Y. So let's see what it's saying. It's applying force P at corner B, okay? Knowing that the crate starts at to tip about E right here. When A equals 200 millimeters, okay, so they're telling us that this starts to move to tip when this is 200 millimeters. That's why A is given at 200. So A, what is the coefficient of kinetic friction? So mu sub K between these, the floor, the ground, and the box, and what is the value of P. Okay, so this is an interesting problem because we're gonna have to use this distance to find the kinetic friction. So the first thing we have to do is to take into consideration all the forces that we need. So let's go ahead and use algebra and trigonometry to find our system of forces, or free body diagram. So the first thing we have is, let's use the box as a reference. All right, so we know the dimensions of the box. We know that is 0.9 meters, or 900 millimeters, and 1.2 meters. Okay. So from here to here, 0.9 meters. And from here to here is 1.2 meters. All right, we have that. That's the simplest thing. Okay, we also know that there's a force W that is given by the weight, and we know that there's a force P with respect to the horizontal axis, and that was 15, that was to 15 degrees. All right, so if you try to move those forces together, you can translate the forces. Remember chapter 1. You can rotate, well, not rotate, but you can just move them around until you find a parallelogram. You have that system right there. The forces are meeting right there. If you have a perpendicular force to P, so I'm starting to get pretty crowded. So let's do P, W, and a perpendicular force to P. So this is 90 degrees. And we are told that this angle right here is 15. Therefore, this angle right here is 15. Okay, so we already have that information right there. So let's go back to our box. Our box is right here. And we're going to use that 15-degree angle to find some interesting information. So we're going to have P. Let us exaggerate P a little bit. So that angle is 15 because it's just complementary. So this angle is 15. Then we have a straight line down, perpendicular. And then we have W. All right, so if you notice, we have some things that we know right here. This one right here is 90. Therefore, if we call this alpha, let's say, alpha is equal to 90 minus 15. That is equal to 75 degrees. So this angle right here is 75 degrees. The only thing we have to know now is, well, what is this angle right here? This angle right here, because that angle is the angle at which is going to tip. All right, so let's see, to find that angle, what points are we given? We're given A, B, C, and D, okay? So let's call this point, how can you call this point? We can call this point, not P, let's call this point, I don't know, L, anything that we're not using, L, and this point M. LM. All right, so from there, we know that the point, that distance LM really is 0.9 meters. We know that by now. But if we bring that over here, which that's L and this is M, and we have an angle right here that we're trying to find, we know that this right here is 1.2 as well. 1.2. So the middle point is at 0.6. And this is A, so A, therefore this is 0.4. Okay, so let us use that information from the edge of the ground floor of the dock of the ground before it starts tipping to our point L. So at that point right here, it'll be 0.4 meters. This one is 0.9 meters. So if what we want to do is to find the angle, well, let's see something here. We can actually find this point right here. So we're gonna need another distance. We're gonna need another distance. So this is L, and let's call this point O. So what is this distance from here to here? The distance OL. We know that this is 15. We know that this is 75. So we can find this pretty easy because we have two angles and we have a distance of 0.6. So in other words, if we do it over here, we have a force P and angle of 15.0 point L. From here to here is 0.6 meters. What is this? We can find it pretty easy because we have this distance and that angle, so we can do either side, finding this hypotenuse, or if what we care about is this value, then we can do tangent, because this length with the angle of 15 gives us a tangent. So in other words, tangent of 15 degrees is equal to y, or in this case OL, divided by x, which is 0.6. So 0.6 meters times tangent of 15 degrees is equal to OL. So that distance is tangent of 15 times 0.6 is 0.16. So this distance OL, 0.16 meters. So this is a virtual point, a point outside of the box, where we're extending P will have a point of intersection with the perpendicular value axis. All right, let's see. Okay, so now the point LM is equal to that distance. Well, let's see, the point OM is equal to LM plus OL. Basically, this distance of the box, which we know is 0.9, plus that distance, which we also know, which is 0.16. So 0.9 plus 0.16 is equal to that plus 0.9 plus 0.9 is 1.06. 1.06 meters. All right, so we have the point OM. Great, that's the distance between that external point and the point M. So with that, we can find this angle theta, and that's the tipping angle at which this force P is perpendicular. The perpendicular force to P is at this angle from the weight, from W. All right, so in that case, what we can do is say tangent of that angle is equal to the opposite, which is this right here, 0.4. So 0.4 divided by what we just found out, which is 1.06. Then we're saying that the angle is equal to tangent inverse of 0.4 over 1.06. All right, so what is that? 0.4 divided by 1.06 is 0.377. So tangent minus 1 of 0.377, and that value is in degrees. What is going on here? What? Oh, it's my tangent inverse. I'm sorry. Tangent inverse of 37.7 in degrees. 37 of 0.377 degrees. How come I always get issues with, oh, 20.66, I saw it right there. I saw it before I pressed enter. Let's try again. Yeah, tangent always gives me a hard time with this search engine. Tangent negative inverse of, what is going on? Equals. All right. Tangent of, what happened here? Tangent inverse of 0.377. Well, what about Google? Tangent inverse of 0.377. 20.66. I am not sure what happened there. So this is equal to the angle is 20.66 degrees. All right, so basically we have the information needed for building the system of the pre-body diagram, which we're going to do right here. So we have a force P, which is meeting with force W because of the weight of the box, and that force right here is what we're moving to this point right here. Okay. All right, so we know that if we have a horizontal line right here, we would have that this one is 15 degrees. This one we already know, which is 75 degrees. And we can find, well, we can find anything else, because if this one is what we just found, which is 20.66, right? We found this one, therefore we know this one, 20.66. Therefore, we can find this angle by now, because we have that 180 minus 75 minus 20.66 degrees is equal to, let's see what that is equal to. So 180 minus 75 minus 20.66 is 84.34. So this whole angle beta is equal to 84.34 0.34 degrees. So now you see why we wanted to form this triangle, because now we can do the law of sine. So P was given, P was not given, but the force given the weight is given. So what we have right here is that the weight is 50 kilograms. So this is W, so 50 kilograms times 9.82 meters per second squared. This is equal to 50 times 9.82. Let's say 9.81. 490 newtons. 490 newtons. So we have a triangle where this is 490, this is 20.66, this is 84.34, and this is 75. So we're going back to the law of sine. We use that all over statics because it's very convenient. So if we want to know P, then 490, the sine is 84.34, and P, sine of that is 20.66. So let's see what we get when we do that. So P over sine of 20.66 degrees is equal to 490 divided by sine of the opposite angle, which is 84.34. Okay, therefore P is equal to 490 times sine of 20.66 divided by sine of 84.34. So sine of 20.66 divided by sine of 84.34. That is 0.354 times 490 is 173.7. So 174 newtons. So this force right here, P, is equal to 174 newtons. And they were asking about, actually the first question was the coefficient of friction. So how do we know what is the coefficient of friction? Well, if you remember from the very first introduction to friction, we said that the angle, or better yet, the static coefficient is equal to tangent of the angle, and that was here when we mentioned the introduction of laws of friction. So given a force with an angle, you find the resultant force in that angle right here is equal to your the tangent of that angle is equal to your static equilibrium. So the difference between static equilibrium and when there's motion is if the force of friction is equal to this component. If the force because of the friction is less than the component of the pushing force, then you have motion. And when you have motion, then you use the kinetic friction coefficient. So by finding the tangent component of that angle, we find the friction component. So what we have to do here is the friction is equal to tangent of the angle that we found earlier, which was 20.66. And actually we did that already. It was 0.3 something. Let's do it again if we need to. So tangent of 20.66, it's 0.377. Yeah, so this friction coefficient is 0.377. So basically it's taking 37.7% of the normal force to move this box to tip this box off the dock.